Hi, my name is Thomas Schmidt of the Media Informatics group of the University of Regensburg, and I present a paper titled Exploring Computer Vision for Film Analysis, a case study for 5 canonical movies. My co-authors are Alina El-Keilany, Johannes Eger, and Sarah Kurek, as well from the University of Regensburg. Now, the computational analysis of movies in quantitative film studies has gained a lot of interest in research in digital humanities in recent years. Now, just to name a few examples, researchers explore possibilities of annotation for film studies, possibilities of text mining on subtitles and scripts. For the visual image or video channel of a movie, computational methods are explored to investigate colors or shot lengths in movies. And overall, this trend in recent years has led to the framing of the term distant viewing, in analogy to distant reading, to describe large-scale, mostly computational movie analysis. Now, in the same line of research, we also see our project. We focus on the visual channel and on the 3 methods: object detection, emotion recognition, and gender and age recognition, which we regard as some of the most promising methods of computer vision for computational film analysis. The research presented here, however, is purely explorative at the moment. We do not want to answer concrete hypotheses, but inspect the benefits and problems of the methods. For example, uncover if the methods show specific characteristics of different movies and subgenres for our small setting, and what research question we might follow in further large-scale studies. Now, for the first exploratory analysis we perform here, we reduce ourselves to 5 canonical movies of different decades, genres, and also of different visual quality or aesthetics, namely Metropolis by Fritz Lang, Wizard of Oz by the director Victor Fleming, Some Like It Hot by Billy Wilder, Breakfast at Tiffany's by Blake Edwards, and the more modern 2012 blockbuster The Avengers by Joss Whedon. The following table illustrates some of the metadata of these movies. Again, we wanted to use a variance of different types of movies. The reduction on 5 movies for this exploratory study was also necessary just due to the fact that many of the methods we use and we perform are very resource intensive. Now, the running time in seconds that you can see here is an important attribute for our setting, as the next slide will show. All of our methods work on single images, so not the entire video in itself, but on single images. So we applied the following preparation of the data to apply the computer vision methods. We digitized our movies in 4:3 format with 720 to 576 pixels, and we implemented a Python program to extract exactly 1 frame per second of the movies. That means that the sample of one movie for us in this setting consists of exactly as much frames as the movie's length in seconds. So we apply each method on each frame and receive results. So the overall end result one can imagine as a table with each result for each frame per line, of course for each method. Again, we also used a reduction in this case, meaning the reduction on only 1 frame per second to avoid resource problems. However, we still think that this approach leads to good representations of each movie. Please note, however, in the following that for the most part, we report results normalized by length to adjust for length differences among the movies. Now, without further ado, let's get right into the methods and the results. For object detection, we use Detectron 2 by Facebook AI, which can predict up to 80 object classes, like animals or vehicles and other things. And it basically works like you can see here. You receive bounding boxes for detected objects and a detection probability. We set the threshold for detections to 50%. This is actually very low, and you wouldn't do this in a real life system, but it fits our explorative approach that we pursue here. For the object distribution, we focus on detection distributions first of all. The following table shows the most frequently detected objects overall, meaning when putting together all movies together. Not very surprisingly, around 85% of all detected objects are persons or closest connected to persons, like ties. Our impression is actually that the person detection itself works quite accurate. As you can see in the table, other frequent objects that are detected are chairs and books and similar stuff. Now, to investigate if the object detection can uncover specific characteristic of a movie, we compared the frequency distribution of a single movie to the overall distribution. While movies like Breakfast at Tiffany's are rather similar to the overall distribution, we did find some objects that can be regarded as special characteristics of some movies. For example, in this example, for the more modern movie The Avengers, we identified that this is one of the few movies including modern objects representative for the movie, like TVs, which are oftentimes laptops or computer screens, but also cell phones, or as you can see here in this example, airplanes, which are not detected in the other movies. Another example is the movie Metropolis, which is the only movie in which we find clocks as a rather frequent object. Now, the omnipresent and always reoccurring clocks in the movie are actually an important motif of the movie, which is also well analyzed in film studies with hermeneutical methods. So it is, on our point of view, rather interesting that this motif of this movie is also uncovered by applying these computational methods. Now, we'll not go into detail of all the distributions. You can read about the details in the abstract. Again, the overall finding for us is that the most frequent objects are rather similar, as you can see here. Now, while we did not perform exact evaluation studies, as they would be necessary to judge the performance of the method, we did explore the performance heuristically by just analyzing the data for ourselves. Our impression is that most detections work surprisingly well, and also if mistakes happen, it is most of the times rather understandable. A good example for this is the object dog, which is one of the most frequent objects in Wizard of Oz, which is, if you look into the data, actually a false prediction more or less. It's the Cowardly Lion, a character of the movie, which is falsely detected as dog. But it's understandable why the object does this detection. Another main problem we actually see is that the AT object classes do not represent a fitting selection for our movies. So many important objects are ignored as they are not part of the possible object classes. There are methods for domain adaptation which are necessary of many annotations of novel objects. However, due to the vast variance of objects in movies, we see the most potential for this method when reducing corpora to a very specific genre of movies. Moving on, for emotion recognition, we use the facial emotion recognition module by Gottfeller et al., which is trained on over 35,000 images to predict the 6 emotion classes: anger, disgust, fear, happiness, sadness, surprise, and neutrality. This is a 2-step process, starting with a face detection, then followed by the emotion detection. The output is a value between 0 to 1 for each class. The values sum up to 1. In this example, for example, the model mainly predicts surprise with 0.95 and a bit anger and fear. We calculate these results over all frames and then build averages for all movies, which leads to the following overall result. Now in this table, the average across all movies is marked, and I will focus on this. The average is of course always quite small, since most of the time values for a single emotions are 0. So it only makes sense to compare the emotions to each other instead of interpreting the data isolated. One thing these results show is that disgust and surprise are rarely detected at all, especially disgust, which rounds to an average of 0 and has a very low maximum of 0.22. For this reason, I will also neglect these two classes mostly, since they seem to play not much of a role in our movies. When comparing the movies to each other, again, I just want to focus on the averages across movies. It is striking that two comedies, or more positive movies of our corpus, the musical Wizard of Oz and the comedy Some Like It Hot, have the highest happy value, which seems intuitive. However, the same movies hold the highest values for angry and for sadness, so the movies seem to be more emotional in general. We could not identify that more dramatic and serious movies like Metropolis have higher angry or sadness values than the other movies. One striking result, however, is that the movie Breakfast at Tiffany's has a very high neutral value. Now, in contrast to the object detection for this quantitative data we have here, we did not just settle for descriptive information, but we also performed significance tests. And regarding all frames of all movies as our sample and the movies itself as independent variables. So we compare if there are significant differences between the movies according to the emotion classes. Due to the vast amount of data, we can indeed show a significant difference, highly significant for each emotion class. But looking into more detail, the effects of these differences are rather low. The largest moderate effect can indeed be found for the class neutral, with a significant effect of 0.12. We analyzed this effect with post-hoc tests, but also with some descriptive visualizations, as you can see here in a box plot graph, and identified that it is indeed the movie Breakfast at Tiffany's, which seems to have a high number of neutral detections compared to the other movies. Now, we are unsure about the reason for this result. Of course, if you have this result in mind and you watch the movie, you would find all sorts of examples and explanations on why this movie is especially neutral, but we would probably not have assigned this attribute beforehand to this sort of romantic comedy. While we do feel that the emotion recognition itself works quite fine, one of the major problems is actually face detection. On the left, you can see an example of an object falsely detected as face, and we identified that the model has especially large problems with any sort of headgear or faces that are not looking directly into the camera, as you can see on the right example. Indeed, these models are trained mostly on pictures of faces looking directly towards the camera, which is of course not always the case in movies and therefore a problem for movie analysis. For the gender and age recognition, we used the Python model PyAgeGender. This is again a two-step process, starting with a face detection, followed by the gender or age detection. The gender detection works by assigning a value on a scale from 0 to 1. And for the model, everything below 0.5 is considered male and everything above is considered as female. Now for the age detection, you receive a number just indicating the estimated age. Looking at the overall averages over all movies and the single movies respectively, we identified that the averages are quite similar, around 40 years for all the movies, which is a rather consistent overestimation, since most leading actors in the selected movies are around 30 years old at the time of the movie. Now, again, performing a significance test, we can, however, show that the difference between the movies is significant with a moderate effect. And investigating this in more detail via post-hoc tests, we found that the strongest outlier movie of all the movies is the movie Wizard of Oz, which is also the movie that's deviating strongest from the other movies by having a leading actor that is a child or more or less a teenager. And Judy Garland in this movie gets detected correctly as 16 years old most of the time. One problem, however, of the age detection is, and this problem is actually well known in age estimation, not just in our use case, is that aside of Judy Garland in Wizard of Oz, the model has great problems with children and also with very old people, as seen in this example for children, with the children being highly overestimated. The problem is again the training data of the models, which is strongly imbalanced towards middle-aged persons, so missing a lot of data about children. As outlined before, the gender prediction assigns male to values below 0.5 and female to values above. However, just for the sake of our own interest, we changed this heuristic to the following, setting the thresholds to 0.4 and 0.6 and adding a so-called androgynous class. By this, we wanted to identify faces for which the model is not quite sure what gender the face belongs to or which faces do indeed look androgynous to the model. Looking here at the results and the analysis between the movies, I want to focus first on class distributions on all frames that actually have faces. First of all, as can be seen, for the majority of the movies, male faces are the most frequently predicted. Around 70% for Avengers and Metropolis, which are indeed dominated by male characters, but also around 55% for Breakfast at Tiffany's, which was counterintuitive to us having a female lead character in this movie. The two movies that differ from this area, however, are Wizard of Oz, with a high number of androgynous faces, and Some Like It Hot with a rather equal distribution. For Wizard of Oz, this result is explained by the high number of fantasy characters, for which the model is unsure which gender to assign. Again, this is rather understandable, but also interesting behavior by the model. In Some Like It Hot, it's important to understand the plot that deals with two male characters that dress up as women throughout the entire movie. So, and in various frames, the model does indeed predict these male actors dressed as women, as can be seen in this example, which finally leads to the more equal distribution compared to some of the other movies. It is, however, interesting that in most cases the model more or less correctly predicts the actors as male, even when they are dressed as women, so it's quite unsure. Now, to sum up our first exploration, as I have mentioned, the research presented here is, while very interesting in our opinion, purely explorative. For example, we reduced ourselves to a small sample of movies because the methods applied are very resource intensive, depending on the machine and the GPU especially that you use. Object detection, for example, on one collection of frames can take a couple of hours. So performing large-scale studies has to be planned beforehand. The libraries and tools we use are not optimized to the use case of movies, but more optimized to social media videos, which prove to be a problem. We do, however, first need to evaluate results to make concrete statements about the performance of these methods. On the long run, we do think, however, that these methods offer interesting possibilities, for example, by looking at interactions and correlations between emotion representations and gender. Nevertheless, all our limitations point us towards the problem of annotations. We are in dire need of annotations for machine learning optimization, but also for evaluation. We started to explore this problem or this task with first annotations on the movies, but of course this opens up a whole new set of problems, like what is emotion actually in a movie and so on. So overall, I am finished with my talk. I hope you had fun with the talk, and we would like to thank you for your attention and are looking forward to your questions.